Hello, algebra friends. I have come across the flagship operation in geometric algebra. It's called the geometric product. And it is saying it is defined as the product of vector A with B is the inner product of A and B with the added to the outer product of A and B. Now, having studied tensor calculus for quite a while now, the first time I saw this, I must admit I got the jeebies. I bet Senors Ricci and Levi Civita are rolling over in their graves saying, dude, you can't add a scalar to a vector. It's just, you can't do that. Well, they did, and it's wicked powerful. We won't get to any applications in this. I just want to introduce it and try to understand it a little bit more. So we've got an inner product and an outer of the product, all right? So let's look at uh, from tensor the calculus what that means. Okay, so we've got a row vector here, which we would call a covariant vector or a covector, and we got a contravariant vector, which we just call a vector. And the inner the product of these A and B results in a scalar. So what the inner product is doing is taking, these are tensors rank 1, right? A vector is a tensor rank 1. So we're taking a tensor rank 1 and reducing it in rank to tensor rank 0, which is a scalar. Now, if I do B dot A, this is considered the outer of the product. So I'm taking a tensor rank 1 and converting it to a tensor rank 2, which is this. So that is kind of the analogy between tensor calculus and this geometric the product, but that's where it ends because there's no such thing as this that I know of in tensor the calculus. So let's make up some vectors here, these two, and let's go look at what we can discover about first of all the product. So this is really easy, right? These are orthonormal the basis vectors. So the E1 dotted with E1 is survives. E2 dotted with E2 survive. The cross terms go to 0. And since this is 0, it's just 2 times 3. So A dot B is just equal to 6. So let's go look at that. Okay, so we start with our old friends, the orthonormal the basis vectors E1 and E2. And we write down our vectors. So this is vector A, and this is vector B. Now, I intentionally put B on the y-axis so it's flat so that this would make more sense, or it does to me, rather. So what is the dot product of A with B? Well, it is the projection of A onto B. And you can see here that if I drop a plumb bob such that I form a right angle, then this is the projection of A onto B. And look what length it is. It's 2. So it's 2 times 3. So it's 6. So the dot product of A and B is 6 via this method of dropping a projection onto B. Okay? So now let's look at the wedge the product. Okay, the wedge the product, A wedge B this is A wedged with B. And here are the rules, remember? So A wedged with B is equal to minus B wedged with A, and any vector wedged with itself is 0. So you can see that if we're going to do first, inner, outer, and last, that the E1 wedge E1 is 0, E2 wedge E2 is 0. So the only thing left is this one, E1 with E2 and E2 with E1. And we just get 9 E2 wedge E1. Okay, let's go look at that. Okay, so here's our two vectors. And we want to wedge, we said A wedge B. Now, what that means is that we're going to go A wedge B. So we're going in this direction, which makes it clockwise. And they call that the negative. Okay? So Let's put first. The easiest way to do this is add them together. So this is A plus B. Then you draw a line the segment as parallel to B here, and that would be that line segment. So you go the tip to tip, and then from A plus B, you go tip to B, so it's parallel to A, and you get this. All right. So this A wedge B going clockwise, this is our bivector. So this is the outer, the product. Now, there's an area to that, which is 9, we saw in the other document. So the area of this trapezoid is 9. And what that actually means is that this E1 wedge E2 is also a bivector. So there are 9 of these unit bivectors. This is the unit bivector. There's 9 of those inside this trapezoid. But you notice in our document we had E2 wedge E1. So we had E2 wedge E1, which means we're going clockwise. All right. So let's go back and look at that. All right. So we had A wedge B is equal to 9 E2 wedge E1. Now remember this rule here. So if we swap E2 and E1, we get a negative. So that's where that comes from. So when we did E2 wedge E1, we were going in the same direction as A wedge B. We were going clockwise. When we change that to E1 wedge E2, we're going counterclockwise, which we have to change the sign of it. All right. And there's no such thing as a negative area. So it's just the absolute value of that. So anyway, the product would look like this. The geometric product AB is equal to 6 minus 9 E1 wedge E2. So this is extremely discomforting, but there are many, many uses for it, which we'll get to. All right, thanks for watching. See you later.